through the volcanic exploration. What we have today, we're going to go through the volcanic exploration. I have the reading assigned, so make sure that you go ahead and click on the reading. Scroll up, click on Explore More Resources, and then scroll all the way down to the bottom and click on Exploration, Formation of Volcanoes. Let's open a new tab so we can just go back and forth between the tabs. And what they show you as you get to the exploration, I'm going to go back to the reading real quick, is a volcano setup. So they have some different equipment for you to look at for how we look at volcanoes and study them and kind of see what they're doing over time. So we have our tiltometer here. It's a tilt meter. It's literally like if meters measure things, like a thermometer measures what? Temperature, thermo or heat. What's a tilt meter going to measure? It's going to measure your tilt. And if we're looking at a volcano that could be kind of growing or getting bigger, this tilt meter is going to tell us how that volcano is growing, how the side of the mountain is actually changing as it tilts and does different stuff. So this is just one part of it. They're going to put these tilt meters actually around the volcano itself and see if they can actually catch the land tilting up a little bit. They also have an electric distance meter. If I can click on this properly. There we go. This is an electric distance meter. They would set this on the other side of a valley from a mountain. And so with this distance meter, you would be able to see the two mountains getting closer just by a little bit, just by a little tiny amount, as one of the mountains, presumably the one that has the volcano in it, begins to swell. As it gets bigger, you will get a smaller and smaller distance to your distance meter, and that's going to kind of show you what the volcano is doing. Last thing, an extension meter. This is going to be the same thing as the distance meter, but for use in water. So they put these in water, they create a sound signal. The sound signal travels from one distance meter to the other, and you can tell very precisely how far apart they are. They put these at mid-ocean ridges, and so as the mid-ocean ridge spreads further and further apart, you see in your extensometer how far apart they're actually getting, and you can see how fast the mid-ocean ridge is spreading. So let's go to the Explore tab. When you click on the Explore tab down here, you now see a volcano setup. So we have a volcano near a subducting plate. So we have subduction zone selected. We have tilt meter selected. And then if you hit record, you can see as the lava comes up and starts to activate this volcano, the sides of the volcano are going to expand, and you're going to see the tilt meter start to get readings. And so in January, it has a reading. In February, it has a reading. This is taking quite a long time, over months of time. It's not going to happen instantaneously. Then in March, you get another reading. April, you get another reading. And so at this point, with all this tilt going on, they've gone up from 500 to 3,000. That's a pretty good signal that something is happening in your volcano. It's starting to expand. It's starting to change, which could be a good indicator that you're ready to erupt. And so they show you some tilting that's going on here in this chart. Let's reset this. Oh, that was the distance meter. So let's do the tilt one and record that. We'll skip the animation because it's going to work the same. So there's our tilt meter. Let's go to a hotspot and see what the hotspot does with the tilt meter. It's going to do the same thing. You can see the lava coming up. It's going to expand the actual surface of the volcanic island. And with a good tilt meter in place, you should be able to see some sort of changes here. Not very much. This is just a slight tilt going on here, but you are starting to see some changes. And so that can help you out a little bit. Go ahead and plot those. And let's reset this and go to mid-ocean ridge, and we'll plot this last one. So they got the tilt meter at the mid-ocean ridge. The thing about the tilt meter here, it's not going to change a whole lot because you're not really looking at tilting when you talk about mid-ocean ridges. They're kind of spreading out flat. And so they're taking a lot of readings. The changes are very, very small. And so they're also taking them every single day. So we will see a readout here if we go ahead and plot. But it's a little bit different than the other readouts you were seeing because it's taken daily and your changes are a little bit less drastic. So from all that, we have all our information plotted, and we can scroll down a little bit, look at the location tab, and they're going to show us a couple other things. So a present-day world map displaying the locations of volcanoes at subduction zones, hotspots, continental rifts, mid-ocean ridges is shown here. The plate names are displayed. You may use the interactive key buttons to examine locations at different examine volcanoes at different locations. So here's our map. All the red triangles are volcanoes. You can see all the volcanoes around the Pacific Ocean, the Ring of Fire. We've got a couple up here in Northern Africa, Southern Europe, as those two continents are kind of tearing apart a little bit. And they're sprinkled about here and there, but in general, most of your volcanoes are at your plate boundaries. And so they have them color-coded by plate boundary. The red ones are subduction zones. The yellow ones are hot spots. The purple ones are mid-ocean ridges. And the blue ones are continental rift hot spots, so where continents have started to tear themselves apart. So there's a little bit of everything in here, but there's not anything, I don't think, anything more interactive to do on this page. So now we go to the tracker page, and they just have our data compiled here for us. They've got a little video of the subduction zone and the hotspot in the mid-ocean ridge, and that should set us forward to our questions. Before we start, we're going to do both pages of this today. There's 6 questions, or 6 or 7 on both pages, so I think there's 13 questions total. That's not too bad. So make sure you do both pages. Make sure you hit submit after the end of both pages. You have to submit each page separately or it won't take it. So let's take a look at these. Compare and contrast magma and lava. What's the difference between magma and lava? We talked about this yesterday.
Magma's underground.
Yeah, magma's underground, lava's on top of the surface. So at least give me a complete sentence for that. Magma's underground and lava is magma that has come to the surface and is now on the surface. Number 2, compare and contrast the working of electronic distance meters and extensometers. So if we go back to the lab here, basically they're going to use almost the exact same technology, just different actual fundamental uses. The extensometer works underwater and uses sound waves, where the electronic distance meter here works above ground or above water and uses light. So it's using light where your sensometer is using sound. And in general, that's going to be the difference. One is used above water in the air, and it uses light, and the other one is used below water, and it uses sound, because sound travels better in water than light does. So yes, electronic distance meter is for above ground use with light. It bounces light off an object to find out how far away it is, and the extensometer is for use underwater with sound. Number 3, explain how a tilt meter monitors impending volcanic eruptions. We kind of watch that happen, but it's measuring the tilt of the side of the mountain. And so if the volcano is about to erupt, we would expect that the magma coming up is going to push the volcano outward, kind of cause it to bulge and expand. And so that tilt meter is looking to measure that bulge, and that should show you that your volcano is about to erupt. If your volcano is not about to erupt, it would be really weird if it were getting bigger and like bulging out in different areas. So there's not a lot that could be going on here. What units of measurement are used in the EDM and tilt meter data? Explain what each unit means. So they want the actual units of measurement in the EDM and the tilt meter data. So if we come back up here, our tilt meter, when we talk about tilting, what is something that we normally use to talk about a certain tilt? Yes, and so a degree, it's almost the exact word, the angle, the degree of the angle. So angle, degree kind of works interchangeably. But yeah, So a tilt meter, they're going to be giving you an actual angle. It might be, I think it might be in radians. Let me see. Does it actually tell me here? Let's go back to our exploration here. And let me reset and go back to the tilt meter. And all right, so the tilt meter is in microradians. I thought it was radians, but it's much smaller, microradians. So our unit for the tilt meter is microradians. And if we hit record, it's actually going to do both the tilt meter and the electric distance meter. And as we might have been able to guess, your distance, your units for distance are going to be in meters. So literally, they're just measuring your distance in meters. But your tilt is going to be microradians. So those are your two units for the tilt meter, and the EDM is meters for your EDM and microradians for your tilt meter.
What's the EDM?
Meters. That's your electronic distance meter. So distance is just going to be straight up meters. Number 5, in general, submarine volcanic eruptions that occur along mid-ocean ridges do not pose much risk to human life. Explain why. Why would a volcano erupting in the middle of an ocean not really affect human life or have much risk to human life? Yeah, there's nobody there. And it's underwater. So we don't have any humans that live in the middle of the oceans. And even if we did, we don't live underwater. So the underwater volcano is not really going to affect us very much there. Humans aren't really around. And then number 6, in this exploration, tools like the tilt meter, extensometer, and EDM, which is just messing me up because EDM stands for something different. EDM are used to detect and monitor impending volcanoes. Think about what happens before and during an eruption. What other tools must be used to detect or monitor eruptions? So what are they asking here? Think about what happens before and during an eruption. So with the tilt meter, the extensometer, and the EDM, what other tools could be used to detect or monitor eruptions? What might we guess a volcano would do before it starts to erupt? It might rumble or shake. So yeah, so like a seismometer, an earthquake detector is actually a really good tool to use. We use those all the time around volcanoes to see if there's any shaking or anything going on. That can help you out. And that could also detect movement deeper underground that wouldn't show up on your extensometer or tilt meter. So yes, seismometer is what you use to detect shaking for earthquakes. What else? What's another thing that you might expect a volcano to do before it erupts? Smoke or bubble. Yeah, you got to have some sort of gases coming out before it's going to erupt. And so we put gas meters there that sense sulfur and other volcanic gases. And so that should probably be good. Those are two really good tools. So a gas detector, looking for volcanic gases that might be seeping out of the volcano, and a seismometer, looking for earthquakes or other movement of land. And when you get that number 6 filled out, and you've got 1 through 6 filled out, hit submit. And make sure you submit this page before you go on to the next page. You don't want to lose your answers or only get half credit. So make sure you hit submit on formation of volcanoes number 1. And let's mosey on over to formation of volcanoes number 2. Number 2. So we got 7 through 13 here. Not too bad. Number 7. Use this exploration to record tilt meter recordings for volcano form to the hotspot. Describe the data. If you were in charge of analyzing the data, how would you interpret it? What does this tell you about the volcano? So we have already done that, but we can look at it again real quick. We're going to a hotspot. We're using the tilt meter, and we're going to record. And you can see as the volcano comes up, our tilt meter is recording. It's going to record a slight tilt. Notice the first thing it records is the same as the last thing. It doesn't change very much. And then at the very end, as the volcano gets pretty much primed to erupt, you start to see some tilting 295, and then by April, you're up to 320. And so what I'm seeing right off the bat is this tilt meter on a hotspot volcano isn't picking up a whole lot of tilt. The other one got a lot of tilt at our subduction zone, but at the hot spot, it's not getting very much tilt. Let's see what it reads down here at the bottom. The tilt meter was placed on the rim of the caldera. The tilt meter readings show increasing in slope angle away from the center of the caldera. This indicates that the ground was tilting away from the vent as the caldera was inflating with magma. Use this plot button to visualize the graphics. Okay, so we can see with the plot button that it goes up towards the end. Now, how do we use this to answer the question? What are they really asking us? Describe the data. If you were in charge of analyzing the data, how would you interpret it? What does it tell you about the volcano? So if we look at the data, the first thing I'm going to describe is at the beginning, I don't see a lot of increase. So for the first 3 months, I have very little increase. And you can see that on the chart. The chart starts relatively flat. For the first 3 months, I see almost no increase. And then over the last month, I see a lot of increase compared to what was going on before. And so I see very little change at the beginning and then a lot of change at the end. And the change at the end, the most recent change would signify to me, not that the volcano is about to explode, but that it's becoming more active and the possibility is coming up. So I would say the activity over the last month, in between March and April, suggests that the volcano is becoming more active and that there could be increased risk for a volcanic eruption. We don't know that it's going to erupt. We can't guarantee it. We can't predict a date. But we can say the facts. It is getting more active. The shape of the volcano is changing. And this is a pretty good indicator that it's doing something. And most of the time when volcanoes do something, they end up erupting. That's what volcanoes do. So, number 8, EDM measurements are much more dangerous to take than tilt meter measurements. Explain why. Much more dangerous to take. I don't know. Let's go up and look at the EDM real quick and see what it says. I don't know why it would be more dangerous, but let's find out. It's got to be where they place it. Okay, so here's the issue. So if we read through this side section here, the problem is it says these are manual data collection. So it's not electronic. It's not going to collect data for you automatically and send it to you. Instead, what this means is a geologist must go out into the field to make each measurement. So every time you want a measurement, a geologist has to come out to this machine or bring the machine with them, set it up, and actually make the measurement. And so if you want to measure volcanoes a lot with these, you have to have people actually on the volcano, which does make it more dangerous. And so that's the rub here for number 8. Is it's more dangerous because geologists are required to visit the volcano more often. Every time they want to make a measurement, they have to go visit the volcano. So number 9, EDM and extensometer measurements may show an increase in distance or a decrease in distance before or during an eruption. Why might they show a decrease in distance? So why are they going one over the other? I would think that it would be more likely to show a decrease in distance instead of an increase in distance. So let me look real quick and see if they explain exactly how they're setting these up. Set the benchmarks near the volcanic calderas and then make frequent measurements of the distance between the two benchmarks, which can be something to thousands of meters, tens to thousands of meters apart. It can calculate the distance within a few millimeters. The data is recorded and then graphed. Okay, so it sounds like geologists set benchmarks near the volcanic caldera and then make frequent measurements. Okay, so reading that, let's think about this. Here's what I think that they're doing. I'm turning the lights on. I think what that says is you have your volcano. Isn't that a beautiful volcano? Just like, I'm like Bob Ross. Just a couple strokes and everybody instantly sees a volcano. So what I think is they're setting these extension meters, these distance meters, up on opposite sides of the crater. And so when the volcano is getting ready to erupt, what would you expect this distance to do? To get larger or smaller?
Larger.
Larger. And that's what makes sense. I was thinking that maybe they were setting up one on an opposite mountain. And so then as the volcano gets bigger, I'm thinking that distance gets shorter because this volcano is like flexing out. But I was thinking about it the wrong way. The writing kind of tells me that they're doing this above the crater. So then as the volcano gets bigger and is ready to erupt, it might get wider because we're expecting this to kind of bulge out as the lava comes up. But what they're asking is, during or after a volcano, the distance could get shorter, right? So how could the distance get shorter? And what I'm thinking is, if you have some sort of collapse. So like if I have magma kind of bubbling up here, but then some of my magma spurts out, and this kind of comes down a little bit, and I lose a little bit of pressure inside my volcano, what's going to happen is I'm going to have a collapse. And if my caldera collapses, these sides are going to move in a little bit. Even if the whole volcano doesn't collapse, even a small one would see the volcano kind of come back in towards that. And so I'm thinking some sort of collapse or drainage of my magma chamber. And that's probably what I would put there. So number 9, why might they show a decrease in distance? I'm looking at some sort of collapse of the volcano or the caldera, or draining of the magma chamber. So a collapse of the volcano or the caldera, or the magma chamber gets drained down. That could show my distance kind of decreasing there. Okay, well, number 10, what type of volcano is common in East Central Africa? And what do these volcanoes tell you about what is happening to the African continent in East Africa? This is actually a really cool question. So we go to location here. They're asking what kind of volcanoes are common in East Central Africa. So looking at the map here, what color icons do I see in the East Central part of Africa? Yeah, the purple ones are what we're seeing there. There are some blue kind of down here. I guess maybe they're talking more about the blue because that's going to be mid-ocean ridge. Those blue and purples kind of go together. So what we're seeing here in this East Central African section, we're seeing these blue and purple ones. This is actually related to the Middle East and the Arabian Peninsula. And so this is not a good picture. Let me pull up Google Maps and show y'all real quick. This is actually kind of pretty cool. The U.S. has had something very similar. Google Maps. Let's go to Africa. Okay, and now we're in here in Africa, and we're going to go to the satellite picture. So here is Africa. And a quick little geologic history lesson. Saudi Arabia and the entire Arabian Peninsula used to be fully connected to Africa. You can see that this piece was right here. The shapes match up, and this sea is actually not very old. In geologic terms, this is a relatively young sea. This part of the continent used to be attached and was part of Africa. When it pulled away, it actually started like this triple rift. So it tore apart right here, it tore apart right here, and it started to tear apart right here. And so through this entire section, through Ethiopia and Kenya and down into Tanzania, you have a long stretch of volcanoes that are there as the country started to pull itself apart, and then it kind of failed. It never really continued. We're not sure if it's going to complete or not, but right now it doesn't look like it. So they just have this huge valley right here with a lot of volcanoes in it. And you can see that on the map. You can see, it's not very zoomed in. You got a lot of mid-ocean ridge volcanoes here in the, is it the Red Sea? I should have looked. Yeah, in the Red Sea and the Gulf of Aden. And then just below that, on the actual African continent, you have a lot of these blue volcanoes, which is a mid-continental rift, like the continent's actually tearing itself apart. I don't think they're going to show it on the map here, but the United States actually had something very similar happen. It just didn't finish. The continent tried to rip itself apart right here. And so we actually have a string of volcanoes through like New Mexico and Arizona, and this huge valley where, you know, the western side of the country tried to pull away from the eastern side, and it didn't really work out. So, you know, we just have the volcanoes that are left over. There was also one somewhere here in like the Midwest, but it's very old, and I don't remember exactly where it's at. I think it's around like St. Louis, Missouri somewhere, but it's been a little while. So they're talking specifically about the East Africa one. What did they ask, just so I know? What type of volcano is common in East Central Africa? I would say continental rift is the type of volcano that's common in East Central Africa. Continental rift volcanoes. And then what else did they ask? What do these volcanoes tell you about what is happening to the African continent in East Africa? The very eastern side of the continent is in the process of pulling away from the rest of the continent. So that little section off to the side is in the process of pulling away from the rest of the continent. Okay, number 11. Compare the formation of magma at mid-ocean ridges with the formation of magma at subduction zones. So remember, we're talking about magma. This is stuff that's underground. So your melted rock that's underground. And we're actually going to go back to the reading for this to just give a good illustration of what we're looking for here. Actually, it's going to be page 2 if they have nice pictures. We'll see. The problem is your mid-ocean ridge with seafloor spreading. Let's look at this one. Your mid-ocean ridge, where is your magma coming from? Where's it coming from in this picture? Yeah, from underneath. And like underneath is just like the mantle. So it's coming from like the center of the earth, right? Not the center, but it's coming from within the earth. This is melted stuff that was below the surface, and heat is bringing up, and it's just going to fill that gap in your mid-ocean ridge. And so for mid-ocean ridges, my magma is coming up from the mantle. Now, for convergent boundaries, it's going to look a little bit different. And I've talked about this before. I actually talked about it in the very last class. And so we don't have a picture. No, we don't. But when I have convergent boundaries, I have two plates going towards each other. What is one plate going to do? It's going to go down. And as it goes down, what's going to happen to the end of this plate?
It's going to melt.
It's going to melt, and that melt is going to come back up because hot things rise. So in a convergent boundary, the magma that I get is from a melted plate. It's this plate melting and coming back up. In a divergent boundary, the magma that I get comes from within the earth. It comes from your mantle. And so that's the difference between your two types of volcanoes that they're asking about. For a mid-ocean ridge, my magma comes from underneath the earth from the mantle. The mantle is coming up to fill my mid-ocean ridge. For my subduction zones, the plate that's being subducted is what gets melted and becomes my magma. So magma at mid-ocean ridges is from inside the earth in the mantle. Magma at subduction zones comes from the plate, the tectonic plate that's being subducted there. It gets melted and becomes the magma. Yeah, so at mid-ocean ridges, my magma comes from inside the earth in the mantle. My magma is coming up from the mantle in mid-ocean ridges. And for the subduction zones, the tectonic plate that's being subducted gets melted, and that melt becomes my magma. My magma comes from tectonic plates in subduction zones, and it comes from the mantle in mid-ocean ridges. Now, number 12, identify one example each for volcanoes formed at subduction zones and hotspots. So you just need to find what a volcano at a subduction zone is called, or not is called, but like an actual real life example, and a hotspot. The hotspots we talked about yesterday. I gave two examples for volcanoes at hotspots. One was in the ocean and one was on the land. Does anybody remember them? Hawaii is a hotspot in the ocean. Yes, Hawaii's on a hotspot. What was the other hotspot that was on land? Yellowstone. So for hotspots, put Hawaii and Yellowstone. Those are both real-life volcanoes and real-life hotspots. For subduction zone, you're looking for an area that has, let me turn this back on. So, actually turn these off. You're looking for a volcano that you know in an area around here. Do you know any volcanoes around here? What's the one that we talked about a lot up here in Washington State that blew up in 1980? Yes, Mount St. Helens. That's a subduction zone volcano. So put Mount St. Helens for subduction zone. Yes, did you say Fuji in Japan? Yes, Mount Fuji in Japan was the other one I was thinking about. That is your classic subduction zone volcano. So those are your two. Fuji and Mount St. Helens for your subduction zones, and Hawaii and Yellowstone for your hotspots. Number 13, last but not least. Use this exploration to record tilt meter readings for volcanoes formed in subduction zone. Describe the data. If you were in charge of analyzing the data, how would you interpret it? What does this tell you about the volcano? It's pretty much going to be the same answer as before. You don't have to answer number 13. We've already answered that essentially. It's just the same thing for a subduction zone as a hotspot. The data would look a little different, but it's leading us to believe the same thing because the volcano is actually erupting in the picture. So, yes, do 1 through 12. Make sure you submit both pages. Hit submit on both pages. Hopefully you already submitted page 1 when you got done with number 6. When you get done with page 2 and you get done, hit submit and you should be good to go. And that's the final assignment for the 5th 6 weeks. We have only 5 weeks of school left. What? Yeah, seniors. Well, I mean, you still got stuff to do. If you want to be technical, I guess maybe you could technically say